Let's continue. We have gone through the very simple code, which is called Section3. Basically, the code offload the computing to the GPUs, and it's done. It's a kind of sequential code. Nothing is complicated. The host side, I mean, the part that's going to run on the CPUs. They need to take care of the GPU, and then they need to take care of something else. But nothing is complicated. But things could get complicated. Let's start from this one. This is the copy, the recopy of a one-page slide in section 1, parallel computing using MPI. We won't dive into the details of this piece of code because that has been done in section 1. If you are interested in the details of this piece of code, please go to section 1. But here, what I'm going to focus is on the communication part of this piece of code, this piece of MPI code, the message passing interface, MPI. So basically, if you look at this code, what it does is that at some point, the code has to call the MPI function to sum up the psums, because each node has to work on a piece of the total workload. The result will be put in a variable which is called psum. So you have as many as psums as your number of nodes. If you are using 64 nodes, you are going to have 64 psums. You need to sum these psums up to have the final sum. So what this piece of code has done is that it's going to make rank 0 to receive the psums from all the others. And all the others, they are going to send their psum to rank 0. Rank 0 is going to receive the psum from all the others. So the rank 0 needs to receive multiple times from, because it needs to receive a message from each other node. So you need to have a loop, and this loop you need to repeat the receive to receive the message sent by all the other nodes. This is the communication, the MPI communication of this piece of code. Basically is, and then the rank 0 is going to sum these psums together and put that in the final result. Here it is. It's called result. And this is the mathematics. No, this of the code. No, it's not math. This is yes, this is the mathematics of this piece of code. This using MPI. Okay, so it works. It works fine. Now suppose that you really have the luxury and you have the chance that your employer has decided to give you some nodes with GPUs, or you are rich enough, your employer is going to hook one PCIe adapter, the GPU adapter, to each of your nodes. And what's going to happen? It's going to be like this. So your node has been changed. Here, this is your node. Your node has been changed. You have a GPU per node. Okay, so I have a zoom in here. You was using this CPU to do your calculation and your communication. And right now, you have a GPU hooked to your system by the PCIe. Okay, that's good. And what's going to happen? Oh, if you do nothing, if you don't modify your code, nothing will happen. Because psum still will be located in the main memory. and the communication will happen. The message, the MPI will happen because MPI is going to take the PSAM from the other nodes. And for example, the MPI is going to take the PSAM here from the mains memory and put it through on the adapter and goes through the network and goes to the node rank 0. And then the rank 0 is going to receive the PSAM and it is going to receive also the other PSAMs, and finally is going to do the sum. This is the PSAM and the sum. Okay, everything will be as before. Nothing will be changed. Then what's going to happen with your GPU? Nothing will happen. Your system works. You are not using the GPU. You are hooked. The GPU is hooked to your system. It's doing nothing. Okay. Now it's a waste. What I want to do the computation with the GPU. What I want to do, I want to integrate to offload the integrate to the GPU. You know, integrate is the computation heavy part of your code. It consumes a lot of time. You want to speed up the things. What do you need to do? You want to offload this integrate to the GPU. Fine, let's do it. Okay, so as we have discussed in the Section3 example, what we need to do is that we need to rewrite this kernel function, the integrate kernel function has to be rewritten, Suppose the rewritten kernel function is called the integrate underscore kernel, and is going to be launched on the GPU, because each node has a piece of workload. Each node, they are going to offload their piece of workload to the GPU. And here is the function to offload the workload. You pass to the GPU the parameters to do the thread grouping. These are the parameters to do that. You pass these parameters to the GPU. The GPU is going to work for you, do the workload, and give you the final result will be put. The result will be put in the DSUM here because the GPU cannot access the CPU memory. It cannot put the result here. It has to put here. And as we have discussed as the Section3 example, before we can launch this kernel function, the host code has to prepare the parameters, prepare a lot of things for the GPU. Mainly, the host need to declare a variable and allocate the memory for this variable. This is called dsum, dpsum. That means psum in the device is called d underscore psum. And then you need to copy the psum from p. You need to copy the psum from the host memory to the dsum. Okay, after the job has been done, you need to copy the dsum back to the psum, and then you need to free this dsum, the memory allocated for the dpsum. So that's going to be the workload. That's going to be done by the host code. So these two lines, there are maybe a few more lines, and they could be written in another way. You need to do the arrow tagging, etc., etc. This is a simple example just to show you the things. Before finally we can call this kernel function, we need to prepare the GPUs to execute this kernel function, and the preparation has to be done by the CPU. And this is the piece, the extra lines you have to insert into this piece of code to make this offloading happen. And don't forget that we need to write this integrate function, integrate kernel kernel function somewhere. We have to define it somewhere. Okay. And then we can we copied the dsum, the partial result from dsum to sum. We copied back. It's the string CPU has copied it back. The CPU is calling the memory copy, heap memory copy from device to host to copy the data back to the CPU. And right now, you don't need to modify your codes. You can still do the send and receive. You collect all the p-sums and you do the addition of all these p-sums. You are going to have this final sum. This is offloading of the integrate function to the GPUs. Well, it's not too much complicated, but there is one thing. This is a very simple example. If this p-sum and d-sum, for this example, the p-sum and the d-p-sum are two floating point numbers, just scalars, two small scalars, 64 bits. Okay. Suppose that you are going to have the situation that your dp-sum or your p-sum, that's not a simple scalar value. It could be a two-dimensional array. It could be a very big array. And you copy the data in and copy the data back for the MPI to happen. It seems that it's going to take some time because clearly we know there is bottleneck here. So my point is that if you can copy this p-sum to the GPU and you have the GPU work on that. So if I don't copy the dp-sum back to the CPU, what I'm going to do is that I'm going to call these MPI libraries. I'm going to ask the MPI message send and receive to send this dp-sum and to receive this value from other GP from other nodes. So could that be okay? What I mean is that the MPI is working with p-sum, send this p-sum, and you are going to sum this p-sum up, and you have the final result. What I mean, could I ask the GPU to do this kind of sum of all these dp-sum without transferring the data back to the CPU, and finally you can have this dp-sum in the memory of the GPU, because the GPU can do the computing. And finally, at the very end, you transfer the dp-sum from the GPU to the CPU, and only run 0 need to do this one. The others, they don't need to do. Okay, is that okay or not? So in this case, we can simplify the things. But that sounds okay because you know what? The CPU can access the GPU memory. Okay. So the answer is yes and no. Okay, we need to have a look. Why the answer is a yes and a no? Is a yes and a no. So we have to come back to the fact that the MPI libraries are not always the same. There are, you know, how the MPI library works. How the MPI library work. Very simple. If you are running your code on node with InfiniBand adapters, the InfiniBand adapter is going to use the RDMA feature to access the memory, the system memory, and take the data that need to be sent to other nodes and put that into the adapter and push the data into the InfiniBand network and send to the others. The other side, the receiver is going to receive the data, and the adapter is going to use this RDMA feature and put the data back into the memory, the system memory, and this is going to happen. Okay. Traditionally, MPI works this way, and MPI works only with the system memory. That means if you are running MPI on the InfiniBand, traditionally the MPI library running on top of these kind of adapters, they can only have access to the system memory. It cannot do this. It cannot access this memory. It cannot access this memory. Okay. Even though that later on we have quite a number of features added to the GPUs to support the GPU computing. What I'm thinking is that the UVA, the UA means universal virtual addressing. Okay, that means the GPUs and the system they are sharing a universal virtual address. These are the features added to the system to the GPUs later on. But anyway, if your traditional MPI library implementation, it doesn't care. It doesn't make use of this feature. It doesn't care this one. It doesn't mean anything for the traditional MPI library, so it doesn't work for them. And then later on, we have this kind of GPU direct RDMA supported by the latest generation of GPUs. But anyway, for traditional MPI library, it doesn't care this one. It's not meaning for them. It doesn't use this feature. So it's not used, and it's not used for the traditional MPI library. So for the traditional MPI library, for the MPI communication to happen, the data has to be in the system memory. It has to be here. If you happen to have your data somewhere in the GPU memory, for example, you have PSAM here. The traditional MPI library, they cannot access this PSAM located in the GPU memory. It cannot access this one. It cannot send this variable through the network to other nodes. Okay, so that's the traditional MPI library. And this kind of a library, normally we call it non-GPU aware MPI library. So it doesn't care about this GPU. It's not aware the existence of the GPU. It doesn't work with it. So this is the traditional MPI library, non-GPU aware library, or you call it non-CUDA aware MPI library. For this kind of library, to send a data, if the data is in the GPU memory, first you have to copy the data from the device memory to the host. And then your MPI library can send the data in the host memory to the receiver. The receiver is the same story. The receiver has to receive the data and put the received data in the memory of the host. H means host. So receive buffer in the host. And then if really you need to put this data in the GPU memory, what you need to do is you need to do the copy. You have to copy the data from the host memory to the device memory. That means GPU memory. The direction of copy is from host to device. So the answer no is that for the MPI communication to happen, for the traditional MPI library, which is not GPU aware, non-GPU aware, or not CUDA aware, non-CUDA aware, for this kind of MPI library, to make your code work, you have to copy the data from the GPU memory back to the CPU memory, even though you have to pay the overhead, the data transfer overhead by going through the low-speed PCIe link. You have to do that. That's the traditional non-GPU aware MPI library. You have to do the data copy as it has been shown here. It's not using the features, the UVA features, the RDI, GPU direct RDMA features. Is not meaningful for this kind of non-GPU aware MPI library. But there are also the libraries which are GPU aware MPI library, or you call it CUDA aware MPI library. This kind of library, they work with the situation that you want to send the data which is located in the GPU memory, and the receiver said the GPU can, the server can receive the data sent by another server and put that data back into the memory of a GPU. So the data transfer will be from the GPU memory to the GPU memory. Okay, so this kind of memory is called GPU aware MPI library. So there are all these libraries which are GPU aware. For this kind of library, you can, the answer is yes. You can send the data, and the other side, the server can receive the data. The destination and the origination of the data could be both the GPU memory. Okay, there are some features which is making this kind of CUDA aware MPI library, the GPU aware MPI library implementation easier. These features include this kind of UAV. UAV means universal virtual addressing. These features supported by the GPUs is going to be very helpful for the implementation of the GPU-aware MPI libraries. And this GPU direct RDMA means that the adapter can use this kind of GPU direct RDMA feature and access the GPU memory directly, bypassing this CPU. So these two features are going to make the implementation of the GPU-aware MPI library easier. And in this case, the MPI communication is going to be to happen for the request of sending and receiving data. The sender and the receiver will be taking the data and put the data in the GPU memory. So this is the reason why I'm saying the answer is a yes and a no. That depends on the situation. Because in the real life, we could have the situation that the data need to be sent from the host memory to another node's host memory, and there could be the situation that we need to send a data located in the GPU memory and put it in the receiver's GPU memory. If we have to copy the data from the GPU to the CPU, we have to pay the overhead by going through this PCIe low-speed link. That makes the system not so efficient. Then there comes the request for sending data from the GPU memory to GPU memory, and that could be done with this kind of GPU aware MPI library, but with traditional non-GPU aware library, this cannot be done, and you have to copy that. Okay, we are going to have a rest for 5 minutes, and we are going to come back and then we are going to have a look of the peer-to-peer memory access.